Okay, in this video, we want to look at the concepts of a determinant and inverse. How do you calculate the determinant and the inverse of matrices? So first, let me remind you, or maybe just indicate that if A, which is a P by P square matrix, this matrix is non-singular, and I'll define singularity fairly soon, if and only if the rank of A is equal to P, is equal to its dimension. So in other words, there's no row in A that contains only zeros. Okay? So now we can find the determinant of a square matrix, a 2 by 2 matrix, as follows. Suppose we have 3 and 5 and 4 and 8. All right, let that be A. So in this case, P equal to 2, and we can see, and we do not denote the determinant of A by either a straight line on either side of it, or just simply determinant of A. And in this case, it's equal to 3 times 8 minus 4 times 5 is equal to 24 minus 20 equals 4. So the determinant of that little matrix is 4. Now, in this case, A prime, or as we've denoted it before, is equal to the transpose, which is 3, 5, 4, 8. All right. And the determinant of A transpose, just draw that like that, is equal to, again, 24 minus 20. So, in other words, the determinant, and that's the first property of determinants, is that the determinant of A is equal to the determinant of A transpose. All right. Now this holds not just for P equals 2, but it holds for all P as long as the matrix is square, and as long as it has a rank of P, where P is equal to the size of the square matrix, and that matrix is therefore non-singular. Okay? So the second point that we can write here is that if one row is a multiple of another row, and you can think about that, or column, of course. You can think about that in the way that when you're creating these elementary matrices, and through these row operations, these elementary row operations, if you end up reducing the the matrix so that one of the rows is completely zero, which occurs if one row is a multiple of another row, then you can see that the determinant would be equal to 0. Okay, think about it. You've now got two rows, one of which is a multiple of the other. That means you can eliminate one of them through an elementary operation so that row becomes 0. And if you have a row of zeros, the determinant is 0. And it turns out that A is singular. All right, so then A singularity of A. So A is singular if that were to happen. So before we go on and look at other properties of determinants, let's just begin by solving determinants for matrices, matrices that are bigger than 2 by 4, that have more than 2 dimensions. All right, we're going to look at 3, and it makes no sense to try and look at 4 or 5 or 6. It becomes too difficult. So we're just going to go through and talk about 3 as opposed to greater or higher dimensions. Before we can look at the determinant, we have to know what a minor is. So the minor of some P by P matrix is defined as follows. So first off, we talk about the minor occurring when you, so say you take the ith row and the jth column, and you remove those from the matrix A P by P. All right, so remove ith row and jth column from A. And we denote that as Aij. So this is the ijth minor, and we are interested in this determinant. All right, this is really the minor is the determinant of Aij. So this is the minor of element Aij in A. Okay? Now, we also have a cofactor, the Ij cofactor, of A. A is equal to Aijc. And now, this particular notation varies from one text to another, from one person to another. Some people just use Cij instead of, so they may use Cij. But the point is it's equal to -1, all right, -1 to the power I plus j, multiplying by ij, or equal to -1 I plus j Cij. Pardon me, that's not right. That's not quite right. I'll have to eliminate that off of there. And I'll make that adjustment later. Now, this here is the sum of the row identifier the row identifier plus column identifier. So in other words, if we're looking at the minor of Aij, and let's say that the minor is A32, all right, then minus 1 to 3 plus 2 is equal to minus 1. If the minor is A22, then we get minus 1, 2 plus 2 is equal to plus 1. All right, so that's how we get that component of the cofactor. So the cofactor is simply this term here multiplied by this minor of Aij. Okay, so once we know that, all right, we then can find the determinant of A. So that's equal to A. That's our original matrix, is equal to the sum of J equals 1 to this P of Aij, C, all right, is equal to the sum from I equals 1 to P. So in the one case, we're going over columns. In the other case, we're going across rows. And that's for all Ij. And we also find that the determinant of scalar, so if we have determinant of some number alpha, it's simply alpha. Okay, so now property, is it property 3 now that we're going to look at of determinants, is that the determinant of k, where k is some scalar or constant, is equal to k to the power p times the determinant of A, where A is P by P. Okay, the fourth property is that if A has 2 columns and 2 rows that are equal, this should be or. So if it has 2 columns or 2 rows that are equal, then we get that the determinant of A equals 0. So this is simply a restatement of the more general property number 2 that we had above. All right, so if we look at property 2, if one row is a multiple of another row, or if one column is a multiple of another column, then the determinant is A is equal to 0. And here we're saying if A has 2 columns or 2 rows that are equal, so of course one is a simple multiple of the other, then the determinant is 0. In this case, the multiple is 1. All right, now the fifth property here is if B is produced by interchanging, if B is produced, so a new matrix B is produced from A by interchanging by interchanging, so in other words, changing the order, two rows or two columns of A, then the determinant of B is simply equal to the determinant of A. Number 6, if B is produced from A by replacing one row or one column of A by K times that row or column, then the determinant of B is equal to K times the determinant of A. Now 7, property 7, if B is produced from A by replacing one row or column of A by that row or column plus, and that's the key here that makes it different than the previous one, plus a multiple of a different row or column, then determinants are equal. Determinant of B equal determinant of A. All right, so that number 8. And some of these are not mutually exclusive. We've already seen that that was the case with points 2 and I think it was 3 or 4. A is non-singular. Here we come to this more, to this stronger definition of non-singular, if and only if the determinant of A is not equal to 0 and A is singular, if and only if the determinant of A equal 0. 9, if A is non-singular, and it has to be non-singular, then determinant of A inverse, all right, we write determinant, we write A inverse as A to the power minus 1, and then we have 1 over the determinant of A. All right, that's that one. And the final property here, number 10, is determinant of A times B is equal to the determinant of A times the determinant of B, and we can also write that as A and B. Okay, now the final thing that we need before we can go to the inverse or Cramer's rule is what's called the adjoint. And sometimes it's called the adjugate matrix. and that uses those properties. So if the original, we're going to look at a 3 by 3, A is equal to A11, A12, A13, A21, A22, A23, and A31, A32, A33. If that's our matrix, then matrix of minors of A is given by A minors equals A11, A21, A31, A12, A22, A32, A13, A23, A33, where A, those capital A's were defined above, and then the cofactor matrix, is given by AC, and that's equal to A11C, A21C, A31C, it's not quite right. One, two, A13, A22, A23, A32, and A33C. All right, that's our cofactor matrix. And we use that information to find the inverse of A. All right, so the inverse of A is given by the adjoint matrix, A over the determinant of A, and where the determinant in that is found as indicated above. All right, now a more general version of the inverse rule is Cramer's rule, and Cramer's rule is a much more general version of what we just did. And suppose we have this system of equations, all right, and we can rewrite that system, or pardon me, we can rewrite the solution as x1, xn, where we have n unknowns. That's equal to 1 over the determinant of A times this matrix of cofactors. All right, A11C, A21C, A N1C, and that's all the way down to A1NC, A2NC. And what you'll notice is that this matrix here is nothing but the transpose of that matrix up above. Okay, this matrix here. Okay, and this is the transpose of a C. All right, that's what that is here. All right. We have to then multiply that, of course, by that matrix here. So this is B1 all the way down to Bn. This is the right-hand side of this thing here. That's the right-hand side. And notice that this is n by n, and this one is n by 1. So then the solution is n by 1, because this is just like a scalar or a constant. So we're multiplying a matrix by a constant or a scalar, and then we're multiplying that matrix by a vector. All right, but notice this is the important part, that this is equal to AC transpose. All right, the transpose of the matrix. All right, we're going to leave this video where it is. We're going to stop. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.